Okay. Hello everybody, and hello viewers. Um, Before we continue, I would like to correct something on the OSI reference and model video that we were talking about. Remember I told us that the transport layer, in our transport layer, we have two protocols actually operating there. I said TCP and then DTP. DTP is wrong. It was actually a term that I was thinking of Cisco, and it's actually a protocol anyways, dynamic trunking protocol. But I will talk about it when we start configuring Cisco routers. So, but what is actually the second protocol is the user datagram protocol. Yeah, that's UDP. That's the connectionless oriented protocol. While TCP is the connection-oriented protocol. Having corrected that, I would like us to talk about another topic, which is the genealogy of computer networking. I like my lectures with a brief story so that we easily have an understanding or we easily remember what it's all about. The computer network, as we know it today, actually blended from our mainframes. Back then, mainframes were huge, and the processing speed were relatively slow. So there had to be different versions of architecture before we now came to what they call the von Neumann architecture that everybody is now using up to date. But what happened that made them to develop that was a problem of heat. Before heating, they had intellectual know-how, meaning that it is only privileged people that are intellectuals that could be able to operate those systems back then, which are the mainframes. And the second thing was heat. It was generating a lot of heat because they were using vacuum tubes, and vacuum tubes generally generate a lot of heat. So the system back then it could not be managed. And thirdly, the cost of power. The cost to power these devices were relatively huge and enormous. So at the end of the day, the general cost of having the mainframes was high. So you will have corporate organizations like universities, governments, or a group of entities coming together just to get one mainframe. And because of the ENIAC and VARIAC, I think those were the two flavors that came out back then. One was used for election, while the other one was used for military advances in the US. But they needed more users. So in order to get more users for it, they now decided to come up with what they call dumb terminals. Now, let me explain the concept dumb terminals. We have the mainframe. The mainframe now, we're now connected to an output device which permits me to call the monitor, and an input device, which maybe let's call it a keyboard. So these were the input devices, but located in another location entirely. So because of that, they now have to develop a way of connecting these guys together. That's where networking actually started from. Today we no longer have these things like this, but this still exists. In fact, the very first type of network that you all have there that we used to play with back then when we just learned networking is a peer-to-peer network. But a problem occurred. And what was the problem? They realized that after a certain length, as this guy tends to infinity, after a certain length, the signal attenuates. Something like this. Signals just die out. Meaning that after connecting this particular server to the end device, they find out that there's no connection, despite the fact that they are properly terminated. So what was the problem? I don't know if you remember our first law of resistance. The formula for resistance. Let me explain that scenario using the formula for resistance. In our secondary schools or elementary physics, we are taught that the formula for resistance is resistivity times length over the cross-section area. Resistivity times length over the cross-section area. This is actually referred to as rho. Often referred to as rho. So cross-sectional area is same thing as pi radius squared, which can also be referred to as pi d all over 2 squared, where d is the diameter of the wire. So they now realize that if the length increases, when the length increases, the resistance of the wire also increases, meaning that resistance is directly proportional to the length. And if the diameter of the wire increases, the second thing is that if the diameter of the wire increases, the resistance of the wire decreases. These were the two case studies back then. So the only solution for networks as at that time was to increase the resistance of the wire. So you now have thick cables. But guess what? There was already a problem. And what was the problem? Cost. To produce those cables with very thick diameter length was enormously costly, because cost of getting copper, which is the raw material, was relatively on the high side. So something had to be done. And what was it? They decided to come up with a small gadget. For those of us that did a little bit of electronics, you realize that there's something called a transistor. I cannot. This was the circuit diagram that they had at that time, or of the particular device. This device was the transistor. What happens is that when weak signals come into this part of the circuit, it is amplified and sent to the other end, vice versa. Meaning that they had to design a box whereby the transistor or the device amplifies the weak signal coming from this end to the other end, and it also takes weak signal coming from this other end and amplifies to this other end. So at the end of the day, they were able to, sorry, I have to take out the diagram. At the end of the day, they were able to place a device in between both systems, and they called this device a repeater. They called it a repeater. So now that they were able to get this, so now length wasn't an issue anymore. They could be able to send a lot of different links just having these repeaters. So they now said, okay, why don't we just coagulate or gather them together and come up with just a single box, since it was relatively cheap to produce. So they came up with multiple repeaters in a box, and called this guy a hub. But immediately this happened, they introduced a problem. And what was the problem? Collision domain. I will explain that. Collision domain. What does that mean? It means that everybody was in the physical media. Let me take out this diagram and explain it better for us. It means that what happened was that, let's assume that this was the physical or the hub. the electrical diagram of the hub. And we have resistance, we have resistance, we have resistance. Let's say this is a system. This also is a system. This is a system. And this also is a system. Let's assume that this is the electrical diagram. You understand? What happened is that I told us in our first class that the way a system communicates in a network are just two flavors. The first is that it communicates while it's in a network, and it communicates if it's outside, if the information is meant for someone that is outside a particular network. So, either ways, when this guy sends an information into the bus line, into that physical infrastructure or media, this message goes through this length, and this man sees this message. Remember, I told us back then in networking or communication, there are three types of terms we should understand. The first one is unicast, meaning communication between two individuals, private gist. You understand? While the second one is multicast, meaning communication with a group of persons, clique, what you refer to as clique in a group. Then, while the third one is broadcast, meaning you are talking to everybody, a message meant for everybody. But what this hub has turned this entire network to be is that even while you are sending a unicast, meaning that this man and this man are supposed to be buddies, they are supposed to communicate with unicast. Despite the fact that this guy is receiving the information, the same information is going down to these guys, which wasn't what they intended, because situations like virus or even a rogue can connect to the network and be getting packets that is not meant for it. So something had to be done. And the second issue was that because all the systems were connected to just a single what's the name again? Because they were connected to one single multimedia, thank you. Because they were connected to one single infrastructure, network infrastructure, what happens is that the bandwidth of this particular network was shared evenly between all of them. Let me explain. Take for example, I have a hub, and I have a system, another system, another system. These three guys are browsing with 100 Mbps. Let's assume it's 100 Mbps as the bandwidth of this Ethernet network. The bandwidth that each person will have is 100 divided by 3. Yes, 100 divided by 3. Now, if 100 divided by 3, I say, okay, this is 3, and the other one is, I think, 6 or so. I don't know what the value is, but let's just assume that this is the value 36. I think it should be less than 36 or 33. Can someone divide anything? 33, okay. Let's assume, no, is it 36 or this divided by this? Okay, yeah, 33.3333, yeah, thank you. 33.333, okay. Now, if this active users increases to, let's say, 10, guess what would now be the bandwidth? 100 divided by 10, which is 10 Mbps. You can see that when the number of users were fewer, the bandwidth per person was larger. But as the number of users increases, the bandwidth reduces. That became another problem. So something had to be done with this network regarding a situation whereby scalability was an option. So they now decided to come up with another box. They decided to come up with another box. But on this box, this time around, they now came up with a register.